Chapter 3 is going to deal with stoichiometry and questions like this, and it's going to be really simple if you pay attention. So let's get started. So first, let's go over chemical equations. And reactants, there's two things you need to know, and they're going to be reactants and products. Reactants are things that react, and products are things that form, right? So a reactant is technically going to be the ingredients or what's used up, and products is going to be what comes after, or what is made from the reactants reacting. So think of the reaction occurring from left to right. Reactants are used to make products. So reactants are the ingredients. So say we have bread, lettuce, and meat. Bread, lettuce, meat, cheese, and tomatoes. Those are going to be the reactants, and the product is going to be a sandwich. So product is what's made at the end. So coefficients show the ratio of molecules or moles. Subscripts show how many atoms are in a compound. So we'll show that later. Atoms are rearranged; they cannot simply disappear, meaning that if we react carbon dioxide, which is CO2, um, the carbon and the two oxygen atoms can't just disappear. They're going to be present somewhere else. It doesn't matter if the carbon and oxygens are broken apart. There's still going to be one carbon and two oxygen atoms. No matter how you rearrange them. So, as we mentioned before here, coefficients show the ratio of molecules or moles. So we take this combustion of hydrogen here. We see that 2 molecules or 2 moles of hydrogen gas react with 1 mole of oxygen gas. So this is typically a ratio. That basically means like 2 hydrogen gases react with 1 oxygen gas to form 2 moles of hydrogen monoxide. You can scale this up as well, but we use the simplest whole ratios. That's the same thing as saying 4 moles of hydrogen gas react with 2 moles of oxygen gas to form 4 moles of water. You can scale this up however much you want. This is just the simplest ratio, basically stating the simple ingredients to form just one reaction. At the simplest core, these are molecules, and we'll get to what moles are later. Which moles are just groups of atoms or molecules, or a specific amount of moles or molecules. Um, but it's important to note that, as we mentioned before, the law of conservation of mass, these 2 hydrogen atoms, or these 4 hydrogen atoms, because there's 2 H2s, are going to be present on the other side. And as we see here, there's 2 H2s. They can't just disappear, and that's impossible. So balancing equations, there must be the same number and identity of atoms on each side. Only change coefficients, never change subscripts. And I was confused on why this was for a while, but it's simply because hydrogen gas, which is 2 hydrogen atoms bonded together, if you change the subscript there to change the amount of hydrogen atoms you have, you're changing the molecule. It's no longer going to be hydrogen gas. So, if we have like H2O, which everyone knows what that is, if we add 2 hydrogens, we can simply just change the subscript or the coefficient, and that just means we have 2 water molecules. Now you have 4 hydrogen atoms without changing the fact that you still have 2 water molecules. If you just added 2 water molecule or 2 hydrogen atoms right here, this will become a completely different molecule, and it will be much harder to react. And that just messes up the whole thing. So simply put, the coefficient changes the amount you have. The subscript is how much you have in each molecule. So steps to balance, and we'll show you an example right here. So you write the products and reactants on both sides, and typically that's going to be done for you. They're going to say like, and if it's not, they'll tell you what to do. Like they'll tell you what to react. But first, we balance the most complicated one first, and we use the smallest whole number coefficients. So let me just go back here, and let me just take a picture of this, and let's go over here to Sketchpad. I'm sorry, there's some statistics on here. But we have here C3H8 plus oxygen gas is equal to H2O CO2. And you're going to learn about the different types of reactions that are most common in chemistry in the next lesson. But here we're just going to do that. So first, let's deal with the most complicated molecule. And it's going to be C3H8 here. You can argue that it's H2O or CO2, but for me, this looks the most complicated. So first, you're going to set this as 1. So now it's important to note that we have 3 carbons here and 8 hydrogens here. Now on the other side, we match the complicated atom. So first we can match using hydrogen, or we can match using carbons. I would match using carbons simply because this is an odd number. This is a weird number. You can start with either one, but I would always like to start with the simplest whole one at the side. So since this is only one, we can just simply put 3. And now we have 3 carbons and 6 oxygens because each carbon dioxide molecule has 1 carbon, 2 oxygens, and we have 3 of them. So it's simple math, 6 oxygens. And then we have oxygen gas here. And we'll see what we need. So here we have 6 oxygens, and we have 0 oxygens here. So since each O2 molecule contains 2 oxygens, we're going to need 3 of them to have 6 oxygens. But now there's an issue here, and it arises because of right here. We need 8 hydrogens here. And if we change the amount of hydrogens, it's also going to change the number of oxygens. So it's not really an issue. So we're going to need 8 hydrogens on the right side because there's 8 on the left side that we need to account for. So we have 8 hydrogens. I'll just write hyds. And we have 4 more oxygens. So if we add them together, we have 10 oxygens, and therefore we need actually 10 oxygens. So we just change the coefficient here to 5. And now we have 10 oxygens. And to finally check if your stoichiometry or reaction coefficients are correct, simply see if you can cancel everything out. So we have 8 hydrogens that are reacted, 8 hydrogens that form, 3 carbons reacted, 3 carbons on the right side, 10 oxygens and 10 oxygens. And that is simply the beauty of balancing chemical reactions.